Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the mathematical definition of discrete random variables. In the video on the overview of discrete random variables, we explained that a random variable is a little bit like a car in the sense that the motor of a car is something that's super complicated, but you don't really need to understand it in order to be able to drive, right? You just use the steering wheel. In the same way, the mathematical definition of a random variable in terms of probability spaces is kind of complicated and daunting, but you don't need to even know about it to manipulate random variables using the probability mass function and also estimate them from data because you just estimate that probability mass function. However, just like when you drive, it's good to be aware that there's a motor and know a little bit about it, because what happens if your car breaks down, if you have to talk to your mechanic and you don't want to be ripped off, in many practical situations. Just in the same way, when you're dealing with random variables in probabilistic models, it's good to know that at the end of the day, as mathematical objects, they're defined in probability spaces. And also you might want to look into a book on probability theory to check how to, like some properties of a model or something like that, and you're going to encounter this mathematical definition. So here we're going to provide, hopefully, an intuitive description of that mathematical definition. That's the goal of this video. Let's get started. Our goal is to, when we're using discrete random variables, our goal is to model uncertain quantities that take discrete values. Those are finite or countably infinite. Some examples could be the number of students attending a class, the number of goals scored in a soccer game, the number of earthquakes in San Francisco over a year. We represent these objects, these uncertain objects that can take different values, as random variables. Our notation is that when something is deterministic, you could just replace it by a number. It's always going to be equal to some fixed value, even if you don't know it. We don't write a squiggly line on top. But if a quantity is uncertain, we want to model it like a random variable. So it would have different possible values with different probabilities. We put a squiggly line on top so that we know that it's random. Okay, that squiggly line is called a tilde. Deterministic variables, again, represent fixed values. Random variables represent uncertain values. We never say the random variable a equals 3. What we say is the probability that the random variable a equals 3 is 0.5 or whatever it is. So what is a random variable? If you remember from the overview, depends whom you ask. A data scientist will be like, oh, it's just an uncertain variable that I put into my model. I describe it with probabilities estimated from data. A mathematician, however, will tell you that it's a function mapping outcomes in a probability space to real numbers. So here we're going to actually see what the mathematician means by that and how it connects to what the data scientist is talking about. The best way to start is with an example. We're going to look at a situation where you roll a die twice, and we have a probability space representing these two rolls of that die. We can represent the outcomes in this probability space by the two rolls, which we can put into a vector. Okay, so this would be the outcome of the first roll, the outcome of the second roll. And to get an outcome, we always roll the two die. Okay, so we always get these two numbers. We get a two-dimensional vector. Each of these outcomes can be equal to 1, 2, 3, 4, 5, 6. Okay, so you can think of the sample space as a 6 by 6 square if you want. 6 by 6 matrix, I don't know. So our quantity of interest here is going to be the result of the first roll. And we realize that we can represent our quantity of interest as a function of the outcomes. Okay? And that's what a random variable actually is. A random variable is a function that maps the outcomes to real numbers. In this case, it takes this outcome, which is this two-dimensional vector, and it extracts the first entry, which is a real number, and that is going to be the value of the function. So when an outcome is produced in the probability space, you remember that probability spaces, we always think of them as an experiment that is repeated many, many, many times. When the experiment happens, automatically we get a value for the random variable. Okay, so the range of a random variable, realize that a random variable is a function. So it maps a sample space to a discrete set of possible values that it can take. So the possible values that it can take is the range of that function, because that's what it maps to from the sample space, which is kind of weird the first time that you see it, right? Because these are the possible values that the random variable can take. Why are we calling this the range? That's the reason. It's this mathematical reason. It's this, but you can just think of it as the set of values that it can take. In this case, what is the range of our random variable of interest? Well, it's 1, 2, 3, 4, 5, 6, right? Because those are the possible values of the first row. Realize that those are the values that it maps to, because it extracts the first entry in this two-dimensional vector. Okay. You might have been wondering, and this is something that we didn't address in the overview video, why on earth we're doing this? Why don't we just define PMFs and, use PMFs and move along with our lives? The reason is that, well, part of the reason is that probability spaces allow us to define many different random variables within the same probability space, which makes them interconnected. It allows us to model their dependencies. So in this case, we could define another random variable that captures the value of the second row. Okay, this function now would just take this two-dimensional vector and extract the second entry. We could define another random variable that represents the sum of the rows. Okay, and this function is the first entry plus the second entry. Now, when we obtain an outcome from this experiment associated to the probability space, it automatically fixes the value of all the random variables. So if we get a 3 and a 4, the first random variable is automatically equal to 3, the second random variable is equal to 4, the third one is equal to 7 simultaneously. So that you can start seeing how this allows us to model the dependencies between them. If this one is equal to this, then that one, what's the probability that this other one is equal to something else, That's the kind of thing that arises very naturally from this mathematical definition, even though it might seem a little bit obscure. So again, the outcome fixes all the values of all the random variables defined on that same probability space simultaneously. And that's really important. We're going to talk much more about this when we talk about models that contain multiple random variables. So it's very useful to represent dependencies between uncertain quantities. In case you're wondering, why are we going through all of this mathematical stuff? This is part of the reason. So as we said in the video of the overview, and I mentioned briefly at the beginning of this video, the probability mass function is really what we use to manipulate random variables. It encodes the probability that the random variable is equal to any value within its range, any of its possible values. Mathematically, what is this equal to? Well, it's the probability assigned by the probability measure of our probability space to the event that contains all of the outcomes that are mapping to that particular element of the range. Let's take a look at a picture. Well, before we look at a picture, I will say that, as we will see, this characterizes completely the behavior of the random variable. So we usually say that A is distributed according to its PMF. The PMF completely characterizes the random variable. Before we see the example, a mathematician might ask, wait a minute, you're happily defining these probabilities. Are you sure that they are well defined? Well, let's take a look at the example. Finally, we're going to have this sample space, this is a Venn diagram, right? So this is a square that has area 1, and then inside any shape representing an event will have a probability that is equal to its area. So the random variable maps points here, all of the points here, it maps them to the same value, A1. Any point here, okay, I drew too many lines, but now I'm committed, so let's go for it. It maps them all to A3. And now I'm going to just write 3 points here because I'm being lazy. These 3 points here, it maps them to A2. Okay, so hopefully you see that the probability that the random variable is mapped to A3 is essentially the probability that we get an outcome that is within this square. Okay, and that's what we're talking about in here. Okay, this is what we mean by this event. That probability is going to be the probability that the random variable is equal to that particular value of its range. And now the question was, why does the probability measure necessarily have to assign probability to that event? And the answer, as we'll see in a moment, is that we impose that that's the case. Otherwise, the random variable is not a valid random variable. Okay, but before that, let's take a look at what the PMF actually means within this context. Well, how do we build the PMF? We basically say, what's the value of the PMF at A1? Well, whatever the probability of this event is. What's the value of the PMF at A2? Whatever the probability of this event is. And what's the probability of the random variable at A3? Whatever the probability of this event is. Remember that this is a Venn diagram, so what's the probability that the random variable ends up at A1? 1/4, right? Because that's the... I should have given you some time to think about that. Sorry about that. That's the area of that small square. What's the probability that it will end up in A2? 1/2, because that's the area of this rectangle. What's the probability that it ends up in A3? Again, 1/4. Okay, so that's what the PMF looks like. Okay, so hopefully that makes sense. Again, how do we know that the probability measure assigns probabilities to these guys? We impose it so that the discrete random variable is well defined. So what is the formal definition of a discrete random variable? The formal definition is that given a probability space that has this sample space, this collection of events, and this probability measure, a random variable is a function that maps outcomes within the sample space to real numbers, in particular, to real numbers that are in a certain discrete set. Okay, so it's a discrete random variable. And now we have an additional very important condition, which is that if we look at all the outcomes that are mapping to each of these guys in this discrete set, that group of outcomes, that event, that set of outcomes, has to be in the collection of the probability space, so that the probability measure assigns it a probability. So then we're good. We can talk about the probability that the random variable is equal to A1, the probability that the random variable is equal to A2, and so on. And we impose this in the definition. As we often do, we go from the intuition of what we need to what we impose. So there is some logic to this. If you just see the definition at the beginning, you might be confused by this. But I would argue that it makes a lot of sense why this is in the definition. We call such functions measurable. In case you go, and read a little bit about probability theory, this is what they mean when they say that a function is measurable. Okay, in practice, it turns out that we don't do this at all. We are not going to build a probability space, make sure that the function is measurable, and so on. We just do not do that. What do? We use the PMF instead. Okay, and now we are going to understand why the PMF is enough, why the PMF allows you to just manipulate the random variable. And for that, we have to think a little bit about this, what I call preimages of each of the possible values of the random variable. Let's go to our example again when we have these three possible values, A1, A2, and A3. And what we're going to realize is that if this is actually a function, these these events that map to each of the values, they actually form a partition of the sample space. Let's prove why that is the case. Well, if they're a partition, then their union has to be equal to the whole sample space. That means that if I see an outcome, like an outcome, let's say here, it has to be in one of these events. What does it mean for the outcome to be in one of these events? It has to map to one of these values. But that happens automatically if this is a function. That's what functions do, right? If we define a function from a sample space, which is just a set, to the reals, the function has to assign a value to every element in the sample space. So just by saying that the random variable is a function, automatically the union of these sets is going to be equal to the whole sample space. So we're good. What else do we need for these guys to be a partition? Well, an outcome cannot be in two of these sets at the same time. What would it mean for the outcome to be in two of these sets that map to the values? It would mean that the outcome maps to two different values. that cannot happen because functions map to a single value. That's kind of the definition of function. So again, because the random variable is a function, these events are going to be disjoint. So essentially, implicitly, when we're defining these discrete random variables, we're defining a partition of the sample space. So this is very similar to what we saw when we're talking about how to define a probability measure. Remember that we did this for the 6-sided die, and essentially what we did is we looked for a granular partition that allowed us to represent the sets that we were interested in. We defined the probabilities on those events within that granular partition, and that was enough. Well, this is implicitly what we're doing when we define a discrete random variable. And just to mention, like you see this partition here, if we looked at the partition for a different random variable within the probability space, it would induce a different partition. That's something maybe to think about a little bit. But anyways, okay, so why is this important? This is important, and this is just a statement of what I just said. We have this function that maps to a discrete set. These events, each mapping to each of the values in the discrete set, they form a partition of the whole sample space. And we're going to use that partition to basically reason about the probability that the random variable is in any possible subset of its range. And that's the whole point. So imagine that you want to describe the behavior of the random variable. Typically, the way you're going to describe it is by saying, oh, it's in this subset of its possible values. So if you want to do that, then you're in luck, because you can go back to this partition and represent that subset as a union of events in this partition. So imagine that you want the probability that the random variable is equal to A2 or A3. So this union, how are you going to compute that probability? Well, the events are disjoint. It's just going to be the probability that the random variable is equal to A3 plus the probability that the random variable is equal to A2. But those are already encoded within the PMF. So you can just sum values in the PMF to compute the probability that the random variable is in this subset. And you can do that for any subset because this is a granular partition of the sample space. Let's write this mathematically. We want the probability that A is in this subset S. This subset S is just all the outcomes that are mapping to S. In my example, all the outcomes that are mapping to A2 or A3. Now we can always express that as a union of these preimages of each of the values in the range of the random variable that are in S, okay? Those are the outcomes that are eventually going to map to S. Now we're in luck. These events happen to be disjoint. We can add their probabilities. And in fact, each individual probability is just the value of the PMF at that event, okay? For some reason, I didn't decide not to put a small I here. Sorry about that. The point is that, the point is that if we're going to reason about how the random variable is behaving, we can completely forget about the probability space and just use the PMF. And let's look at an example. I always do this. Okay, let's look at an example in a moment. Before, we're going to state a very important property of discrete random variables, which is that they always sum up to 1. Okay, so if we consider the sum of the PMF over all its possible values, basically this is the probability of the union of all of those events, right? Because all of those events are disjoint, so the probability of their union is the sum of the individual probabilities, and each individual probability is just the value of the PMF for that value. The value for that value, hopefully that was clear, the value of the PMF for each AI. Okay, but what is the union of these guys? They're a partition, right? So the union is the whole sample space, which has probability 1. So every PMF has to sum to 1 because of the properties of this event. We're not in the example that I promised you yet, but we will get there. To model an uncertain quantity, actually now I'm realizing that the example I was referring to is in the video on PMFs, because here we're just going to focus on the mathematical description of PMFs. So look at that video, which I will post very soon. Okay, let's go back to mathematical description, which is what this video is about. Sorry, like sometimes, I get a bit confused. Anyways, to model an uncertain quantity with values in a discrete set A, and we want using a discrete random variable A, this is a big A, and this is a squiggly line A, the random variable, the discrete random variable, we just estimate the PMF because of what I just said, right? Like if you want to describe this uncertain quantity, at the end of the day, you're going to use the PMF. So that's what you need to estimate from data. And the mathematician would be like, okay, sure, awesome. But how do we know there's an underlying probability space? If there's no probability space, everything breaks apart. What are we even doing here? Okay, so yeah, a bit of a dramatic mathematician. Well, what we should tell these dramatic mathematicians so that they calm down is that we can actually build the probability space from the random variable, so it's all good, even if we just manipulate the random variable using the PMF that we estimated from data. How do we do that? Well, if the if the PMF that we have estimated is non-negative and sums to 1, we do need that, right? Otherwise, we're not going to be able to do this. The PMF has to add to 1 and has to be non-negative. But those are the two only conditions that we need. Then we can build a probability space in the following way. We're just going to say, look, the sample space is going to be the discrete set. The collection of events is all the possible subsets of that discrete set. That's going to be the collection of events that we're going to assign probabilities to. How are we going to assign probabilities? Using the probability measure in a very similar way to what we did when we're defining this probability measure for the 6-sided die when we're talking about probability spaces. Let's take a look at what we mean. So we could reverse engineer the PMF. So imagine that we estimate this PMF from data. Then what we say is, okay, so I'm going to build a probability space where the sample space is just these 3 points. Okay, I'm going to represent it like this. Here there's just 1 point, 1 point, and 1 point. The collection of events is all the possible subsets of this set of 3 points, all the possible subsets. That's the collection. It's a valid collection. You can check. And now what is the probability measure? Well, I'm going to say that within this collection, the probability of this guy is just the probability, the PMF at A3. The probability of this guy is the PMF at A2. And the probability of this guy is the PMF at A1. And now to get the probability of any other event in the collection, you can express them as a union of these events that are disjoint. So you just sum those probabilities, which is essentially what we do when we use the PMF to reason about the values of the random variable. And you can check that that's going to give you a valid probability measure. However, we never do this. We just manipulate the random variable using the PMF directly. Okay, so what have we learned? We have learned that the data scientist might say that a random variable is an uncertain variable described by probabilities that we estimate from data. And the mathematician is saying something that sounds completely different. It's a function mapping outcomes in a probability space to the real numbers. But what really happens is that this mathematical definition is designed so that the corresponding object can be described using probabilities that are encoded by the PMF. So they are both right. It's just that the mathematician is telling you about the mathematical implementation that remains under the hood, whereas the data scientist is telling you how we actually manipulate discrete random variables in practice. And that's all I got. Thank you very much.